Thanks, Susan, and again, welcome. So I will start with a survey result, which we have been doing at the beginning of the year. And what we could see on this slide is on the horizontal axis, short-term challenges, the vertical axis, long-term challenges. And we see actually a couple of patterns, which brings me into the picture of what we used to call the magic triangle. Now, the old magic triangle, which I'm sure you know from your PMI, is about the content, the cost, and the quality or the pricing. And the time and cost would always be impacted by how much you do. So it's called magic because the three poles influence each other. Now here we have the same pattern. We have competence on the upper right, we have innovation, and we have on the bottom, let's say, the classic poles. And that is exactly what I call the magic triangle of the new normal, because we are today in a situation where we are heavily fighting to be perceived as innovative, new products, new markets. At the same time, we have a competence gap worldwide on IT experts, and we have all these legacy topics with complexity, with quality, with cost. And that means we need to manage this magic triangle in a similar way as we had the old one. The old one was satisfied with agile. Now we have to see how can we manage in this magic triangle. And one aspect which I'm going to present you today is about better utilizing external experiences on topics which normally would eat a lot of time and in many cases would even be not so helpful to really facilitate. Now, for those of you who are interested to participate in the survey for the next year, it's still open. So you find the link at the bottom, which is our company, www.vector.com, then /trends-survey. It takes not only 2-3 minutes, so it's quite easy to do. Now let us look into the topic which I'm really wanting to bring forward now, which is about liability and the risk which we have in our business. And that holds across industries. And while I'm talking about independent V&V, I will focus specifically on cybersecurity because it's a classic application area. We've been doing independent V&V as a service in different domains. I mean, Vector is known as the test company. We have been developing test tools longer time and so bring quite experience. But here it's about the liability which we have with our products and IT services with respect to cybersecurity. 1/3 of the companies would not have any cybersecurity program in place, or 2/3 test only half of what they are doing. In other words, there are severe risks only from these numbers. And 80% of the code is older than 4 years. And I could continue that list. For instance, if we make a code analysis, which is one of the typical tools which we use, static and static code analysis, software quality analysis, that would indicate exactly this weakness. That is, code is not really tested. And if you test it, often what we see with our customers is that they focus on some areas, but others would remain completely open. So on the one side, there's effort wasted in areas where, you know, the methodology is insufficient. On the other side, there are huge gaps, again, because insufficient methodology. And that's exactly where independent validation would come into the picture, because there is a lot to gain from the experiences which we have from different industries, from different products. And I will show you a few of these examples in the next half hour. One root cause which we see in many of these situations, and I should claim that we are typically only asked if the situation is already quite damaging, but what we see is it has actually not that much to do with tests. It starts much earlier. It starts typically with requirements. And that means about 3 of the 5 failed projects which we look into have a lack of requirements engineering. And in terms of cybersecurity, this is even worse. About 80% of the cyber attack actually only materialize because insufficient focus on security requirements. And that means here's a root cause which goes way beyond the testing at the end. It starts in the beginning to identify what would be negative requirements. I mean, that is one of the topics which many of us are not really familiar with. We think requirements should be functional lists, features, you call it whatever, But this is typically positive. I mean, that shows I have this input, I expect that output. That can be an algorithm, that can be some sort of processing, that can be some sort of reporting. Now, what really happens in practice is that we think not enough about how could our systems, how could our services be attacked? In other words, what are the situations we want to prevent? And that is exactly what we call the negative requirement. That is misuse cases, abuse cases, or confuse cases, the latter being for the usability. And these negative requirements have to be systematically defined and implemented in order to protect our systems. And to make that story short, when we talk here about independent V&V, it actually starts very early in terms of requirements engineering. So I will get you now on a journey through this life cycle, but deliberately start with the requirements part and come every now and then back to it in order to show what can be achieved with independent V&V. And the starting point is what we call the triple peak. Triple peak because we have on the one side the requirements, we have the design, we have the V&V. We typically move from the top to the bottom. That is, we move from the abstract to the implementation. So we have market needs, we have product requirements, we have component requirements. That's something which you learn in each requirements lesson. That is also what is expected to be distinguished, that you have the market requirements which show why you're in business, why you're producing this service, why you're delivering this service. You have the product requirements, which are what you are delivering, and we have the component requirements, which is how you implement. Now, many of us would start only on that bottom layer, which is how do I do my software, but we should start really on the upper layer, which is why am I in business and how would other parties attack me in order to either participate in my business in a negative sense or disturb my business. And that's exactly where also the negative requirements come into the picture. Design is about how do we implement on each of these abstraction layers. I'm not going to go into much detail here because it would be not so helpful. It's not our topic for today. But on the right side, we see that for verification, validation, we have exactly the same abstraction layers. And this is also what we show with these horizontal lines, which is what we call horizontal traceability. Again, often what we see in practice is we start only on the lowest level, which is what are the features of the software, forgetting that there would be also product and market needs. But the same on the right side, we do a lot of the test activities rather ad hoc. That means we do a little bit of unit tests, typically automated in our continuous X tool chain. We do some functional testing, which is pretty much aligned with the features which we implement. And we do some sort of external perspective. What is not done is a systematic exploitation of how could a system be attacked? What would be the weakness of a system? And that is exactly what I want to anchor in our presentation now. So, but the takeaway here would be that have a look into your traceability, because without a traceability, you don't even know what would be your gaps. So often we have customers where we are called either on the requirements or on the testing, but realize what is put here into these red lines is not available. So one example, I have currently a big project where we support a leading supplier for security-based systems. So it's about cybersecurity, but it's of course a normal functionality. And it's a really interesting product which competes with big IT companies, but it's in the IoT sector. And what we realized was they would not really have much traceability. So there was a lot of development done, that is the middle part. There's a lot of testing done, not at all connected really to requirements, and the whole thing would not even integrate. So there's a typical issue which comes rather early. If you just implement software and never think in terms of what would be the complete environment, then it would be really hard to integrate it afterwards. But what is worse is really that when we were called in order to ensure that on the system level, there is reliability, there is robustness, there is also cybersecurity, there was not much anchor points, because first of all, we had to distill the left side with the product requirements and with the negative requirements. How would you attack a system? That is where we take techniques like a threat analysis. And I will show you what that means. Now, the technique which we recommend is test-driven requirements engineering. That means start the requirements and work in the analysis of your requirements immediately with the perspective of how would I test the requirements. That brings two major advantages. One, the requirements are testable. Now, that's an obvious thing if you think about the test cases, but hardly requirements are testable. Hardly requirements are measurable. So it's helpful to think in terms of testability. That's what we put as a kind of a forward test-driven requirements engineering. So you make a requirement, you think about a test case. So if you put your requirement into a tool like Doors or Teamcenter, then you would immediately also ask yourself, what is the related test case? Maybe it's not only one test case. Maybe there are correlations, such as you have an IT service. You want not only to see if the service is working, but you might also want to see is the billing working. What about usability? So that would be test cases which relate to that requirement. Now, with these test cases in mind, we can move back into the requirements and we can identify what would be the analysis and what would be potential solutions. And that is why we use this triple peak abstraction, that we move continuously back and forth between the market perspective or the need, the solution perspective, and the test perspective. So one advantage, as I say, you have the testable requirements. Second advantage, you would have a starting point for your whole test strategy, because that would be a minimum set of requirements, of test cases, which you would then also use for regression testing. And with all this, you would then continue to refine your requirements and your solution model, and of course the test cases from the abstract downwards into what we know already from Agile, which is test-driven development. This is a technique which is around for about 20 years, and that helps to really align the unit test and the coding with specific code-related requirements. So we move downwards from the abstract to the specific. We move back and forth from left to right in order to align requirements, solution, and test. Now that is what we call test-driven requirements engineering. And that's the first, let's say, takeaway out of this presentation, that you have this understanding that you don't want to do requirements engineering in isolation, but you want to do it in connection with the analysis of the solution scenarios and also together with how would I afterwards validate the requirements. Now let us move into the 2-3 major techniques which we are using in the perspective of independent V&V. The one thing which we typically should do in the beginning, independent what the domain is about, is that we do a software quality analysis, SQA. Software quality analysis means we try to identify mistakes in the code, errors in the code. We want to see, are there structures which invite for error or cyberattacks later on, but also we look into how would the code ensure that it behaves in a predictable manner. So for instance, a classic example would be you have loops or you have decisions or you have inputs, and they can be missing, they can be wrong, they can be out of an assumed boundary. So what kind of mechanisms are built in order to avoid that the code would hang up or would run into some situations which are not foreseen. So at no moment there should be any situation where code behaves in an uncontrolled way. This applies for regular IT systems, but even more it applies for safety critical systems like we have in medical, IoT, automotive, spacecraft, etc. Because in these domains, if code hangs, that would be really critical. So from a safety perspective, this is mandatory. From a cybersecurity perspective, it's increasingly advocated, and that means it applies to the whole world of IT and software systems. So what are we doing? We are using, first of all, static code analysis. There are a couple of tools available which are quite good. There are many, in fact, available, but only a few are good. What we expect from the tools is not only that they are suitable for the respective language, but also that you can tailor them according to specific coding rules. For security, for instance, we have the CERT rules, CERT, which help us to have code which is robust. There are different rules available, like for instance, in functional safety, you have MISRA, you have also other coding rules, but they give you already a good basis for creating robust code. And on this basis, we apply the static analysis with respect to code, but also with respect to architecture. So what we typically do in the beginning is not only the understanding of the code structure, because this is really low level, but rather, if I might go backwards a moment, we also want to go back on the more abstract part, which is architecture. So we perform architecture reviews. What are we doing? We make some sort of guided walkthrough with architects to see what are the design rationales. Then we move deeper and see how are they implemented. Then we would do a check with the negative requirements in terms of how have they been addressed. For instance, you want to avoid that certain interfaces could be, let's say, attacked by a buffer overflow. And there are many of these attacks. I mean, buffer overflow have been the #1 security weakness or vulnerability for decades. It's almost on the top 5, independent which application domain you take. That is, we take the architecture analysis in order to find out how have negative requirements been addressed from an architecture perspective. Give you another example. Often cybersecurity correlates negatively with performance. That is, you can harden a system for cybersecurity, you make it slower. So here we have a dependency which is unhealthy, and that also have to be analyzed. So we have different levels of analysis which we apply, but all in all, making sure the code is robust. And in consequence, then also ensuring that we use something which is called defensive coding. And that means we need code which is effective. That means it fulfills the intended functionality, but at the same side, it should also be efficient, so it should be performant. And these are the topics which we investigate with the independent V&V and our software quality analysis. Now, if we move upwards in the abstraction, there would be the randomized testing which we apply. So I leave out all the functional and structure testing because that is typically done inside your design and test organization. And that is useful because that is a white box approach. You are the expert, no need for independent support. But if you move further upwards, it's about behavior in situations which are not desired. If you have a white box perspective, and that's the trap many engineers are in, then you would think that you are invincible. I mean, in a way that nobody would really attack your system because you have thought about everything. I mean, we are all proud to be good software engineers. And as engineers, we think positive. And that means we would not really assume that somebody can attack our system because we just know what we have been doing. But the blind spot of what we did wrong or what we have not been doing, that means the vulnerabilities, that's not really on our radar. So what we do in our fuzzing is exactly to focus on these areas. And here we have different techniques. One is that we just put a lot of data on the interfaces which are accessible. Now you can do that completely black box. You can also do that by some investigation, knowing that what is the system about, what are the interfaces, what components might be used. And that is what we call gray box approach. And this gray box techniques is actually what we have been growing and let's say further investigating the past 5 years, because it helps to bridge between our external knowledge, which is exactly what a hacker might have, what any attacker might have, and the knowledge which is more internal, but which the attacker might not have except for social engineering. And that means we combine all knowledge which is available from an external perspective, be it what interfaces, be it what components, be it known hacks, be it vulnerabilities like recent exploits which have been published. Knowing what kind of components would be used, for instance, helps to see is there a specific Linux version which would be have this and that weakness. And this kind of information, that is what attackers always use. Now we put randomized information on the ports in order to see how can we crash it. Later on, we see also that we put targeted input on the ports, but that would be the last step. So at the moment, we are in the fuzzing. Fuzzing means that we have some sort of fuzziness in our content, in what we really put on the interfaces. It's highly automated. That's obvious because we have to generate a huge amount of different information which we put on the ports. And that means it's a mixture of structured information and randomness. And the randomness ensures that we don't have this blind spot behavior. Structured means we don't need to run all sort of permutations, because that can, of course, be far too much effort. Brute force is not a good advice. That's another lesson learned and take away here. Brute force is very expensive and not necessarily effective. And I show you later on some results from a case study. So what we want to do is really intelligent testing. Try to behave in a let's say in a negative way, like a hacker would do, but with a white hat, as we call it. So it would be a white hat hacker, which use external knowledge, but which is disclosing what we are doing. We discuss it upfront with our customers. Also that they want to learn about it, because I mean, eventually some of the test strategies they should include into their own test strategy. We use a lot of tools, obviously, and I have not the time now to really go into that level of detail, but a knowledge about test tools is quite helpful here, because you not only want to automate, but you also want to have different ways of how you attack the system. Now, going one step higher in the abstraction, that's also the last of the three techniques which I want to amplify here. That is what we call the pen testing or penetration testing. Penetration testing is about targeted attacks on the system. So we try to penetrate the system from the outside in order to get inside, make some sort of changes to data, changes to code, but always through the official, let's call it like that, interfaces which are available. And in order to do that, we have four steps. First would be that we look into what are the interfaces. So we have different methods here, depending how much information is available about the system and about previous exploits. We use what is available. We also dig into what vulnerabilities would specific components have. We would then go into the whole network discovery. So not only the component, but also its environment. That's important for any network device like IoT. Most IT systems are networking. And then we start to get from the outside to the inside. So we start on the network level to perform the penetration test, and finally go into specific vulnerabilities which we detect by means of reverse engineering. And that part I would also show you later in an example, a case study. To summarize on that part, because that is the whole set of methods. First thing was we learned about test-driven requirements engineering. That is that we move from the requirements into testable requirement, having test cases for each requirement. And we move back and forth in order to get more specific. Second, we look into a technique which is called software quality analysis, which helps us to take architecture patterns, software patterns, white box, in order to help our customers to make robust code. Thirdly, we use fuzzing in order to have systematic, not brute force, but heavy data attacks on the interfaces. And four, we have the penetration test. Again, also intelligent penetration test, which is a gray box methodology, taking all information which is available and then attack the system starting from the network level. That is any outside connectivity, and moving as much as we can to the inside. One methodology I want to still show how this all connects together is what we have put into a 10-step methodology. So it's a kind of a cookbook recipe, if I may say so, that at the beginning we look into what are the functionality, what are the components. That's what we call reconnaissance. So understanding what is in the system. And you make a structured analysis, as we would do as an engineer, to understand if I have this function to implement and I have certain descriptions available already for, let's say, in product documentation, technical documentation, online, maybe also by having reverse engineered similar systems in the past, we can analyze what would be now typical attack points in a given new situation. Then we think about what are the assets. That's important because otherwise it remains brute force. What would an attacker really want to attack? And again, that helps really to the independent perspective, because as I said earlier, you need to really think as a hacker, but act as an engineer in order to identify all these attack scenarios. And with the assets, you would then make a risk analysis. That means what would be the outcome, the negative outcome, and how easy it is. So it's not about probability. It's much more about what we call the window of opportunity. Do you need specific knowledge? Do you need special tools? How easy is it to attack a system? For instance, a car can be easily attacked because cars are typically everywhere, and you can easily buy one, or you can just go somewhere on a parking garage and try to impact the car with any sort of tool which you have. Other systems like IT server farm would be more difficult to attack because they are centralized. A smartphone is easy to attack because they are everywhere. So you have different levels of what we call this window of opportunity. On this basis, with the risk and vulnerabilities, which we have prioritized, we would then make a structured risk assessment with respect to what would be the protective mechanisms which an engineer would use. That's what we do with a TARA, a threat and risk analysis, where we take the assets, we look into how they could be attacked, and then we try to distill what would be security goals in order to protect certain assets. With that logic, we have followed the positive way of what an engineer would do. And now we go on the right side and try to find out, so what would an attacker do, knowing about all that? So assuming step 1 through 5 have been done and is possible for anyone from the outside, we then go to the right side and try what would be now minimum set of test cases to just check, are these security goals adequately implemented? And to give you another analogy here about the need of the security goal thinking, which is if I have an asset to protect, like for instance, some key, some information which is stored somewhere in my, let's say in a database, that's what I call the asset. I don't want that somebody gets hold of that or can manipulate it. Then I would see, how would this database be connected to the outside? Does it have interfaces? Can I access these interfaces? And that would be the starting point for the penetration test cases. Now, on that level, we perform test cases. We move backwards and have success criteria, like how effective are these test cases? How much time would I need as the efficiency? That gives us key performance indicators. And then, since we are the good guys, we would enhance the functional security requirements, or if it is independent validation of any other focus, the generic functional requirements in order to better harden the system. So this step number 9 is really what is the difference between the black hat hacker and the white hat hacker, because we help our customers to improve. And that is what is, of course, also the need, what they want to see when we go into the system. And the blue part is now, which kind of methods are we using? I'm not going to read all that, but what you see is a couple of the things which I explained earlier, and that helps us to have a refined methodology, which is really showing a benefit to our customers. Now, rather than reading all this theory, let's see from a concrete case study what we are doing. And I've taken an example from medical because that's something which all of us can somehow understand. And I take an insulin pump, which are increasingly used in practice because people would need periodic dosage of insulin depending on what they eat. And so these insulin pumps are fairly easy to transport. You just carry them in your pocket, and then they would every now and then put a small dosage of insulin into your blood. Now, the structure of these insulin pumps is quite simple from the outside. I mean, there are sensors, there is some controller, and there's then also actuator, which is putting this insulin into the blood. They have typically also some connectivity, and that makes them attackable. Why do they need connectivity? 2-3 reasons are obvious. One is you want to see what they are doing, the battery level. You want to see, for instance, you want also to adjust the dosage in case you are doing some sport where you have to make a change here. Now, with that kind of impacts, you need to have typically a smartphone connection. Another one would be diagnostics. So you go to your doctor or to a hospital, they want to read information about, let's say, logs of this insulin pump. And that would also be a need to access. And with all that, you would, of course, also invite attackers. This would be these black hat guys here. And so what we do now, following our 10-step approach, is that we look into specific aspects, starting with the left side, as I explained earlier, about what is the system, how would I attack the system, what would be then the different, let's say, lessons which I can take in order to create specific test cases. And what I put in blue is now current methodology, how we enhance all that, because the methods which I showed earlier help, but we want, as an independent authority from the outside, also provide guidance. So for instance, we help to refine the requirements. We automatically analyze requirements. We try to identify what would be the weakness. We make architecture analysis. I mean, these are white box techniques, but as I mentioned, white box helps to understand what deficiencies could be built in by the code structure. Thirdly, we look into heuristics. I mean, there are threat catalogs available, which we use in order to identify what have been past exploits, which could be utilized in order to attack the system. We look into vulnerability databases, which are maintained, for instance, by the Software Engineering Institute, and identify for specific components what would be typical attack surface. And we use intelligent testing methods in order to refine test cases, always with the T, to be effective and efficient. Now, this is the result from this specific test which we are doing. Now, what we have been done is quite obvious technique, which we had in the past, which is that we are doing error seeding. So that means one test team would just do the mechanisms which are typically done. Another one would seed errors. And then you can compare based on what different test teams would detect, how good specific methodologies would be. So the seeding is not known to the testers, that's obvious. And now what we look into have been different vulnerabilities, which we inserted deliberately to the code, and then looked into how would a typical internal tester behave out of the company, which is providing such systems. What would be an attacker typically attack with brute force, and what can we detect with a gray box approach? And what we see then, if you compare the traditional in-house on the left side with the independent strategy, is that we need less test case in this independent strategy because it's less brute force, but at the same time, it's also more precise. That is, we achieve with less test cases a better coverage and also a better hit rate of vulnerabilities. And that means we have a much higher coverage. As you can see, we have found a coverage which is 100%, or typically would be in the range of 90 to 100%, because we have this gray box background of the system. So we achieve with a low amount of test cases a wide range of let's say vulnerabilities, which we then feed backwards on the functional design in order to harden the system, in order to make the system more robust. That is the whole methodology which we apply if we use independent validation for cybersecurity. Independent verification, that would be on the code and architecture level, independent validation on the system level. Since I never defined it, let me also give that definition. Verification means that we check if things are done right. That means you follow process, you follow architecture and coding rules. So doing things right would be the target of the verification. Doing the right things, that would be the target of the validation. And that is the abstract external perspective. So validation, system perspective, verification, the white box perspective. Now, if you combine these experiences, what we see is there's no single V&V technique which is perfect. So each one has a good effect. Each one would also have their weakness. And that means we need to combine different techniques. That's another takeaway from this presentation. But we also want to deploy as much as possible this gray box methodology, which is an intelligent analysis. So it's not brute force, it's focused. And we take exposure from previous systems which have been attacked. We take experiences which we bring as an independent company in order to provide a more focused verification and validation, and combining these different methodologies of V&V in the most efficient way. Efficient meaning that we want to spend not so much effort and still achieve good results. Now, to conclude, the message would be, which I pass on also, don't rely only on homemade solutions, which in this cartoon, which I find quite helpful, was when they do all this binaries, they said, we have a new encryption, we put each digit upside down. Now, obviously, that don't make it any change, but we typically are in our own experiences, typically somehow locked. We have blind spots. So we work very much on what we call the known knowns, the areas which we know, but we hardly look into what we don't know, the unknown unknowns. I mean, we are not even aware about what we don't know. And as an independent V&V, or what we also call a security check in our trust center, we bring the experience about how other systems had been attacked, what methods to use. So we broaden the view of our customers from what they know, that they know, into those areas which they don't know, or which they might not even be aware that they don't know them. And more information about that you find here in our white papers, trainings, etc. You will get the PDF afterwards, so no need to make a copy or a picture now. But that would be trainings which are available. We have a lot of white papers on these topics, and we also do have a tool for the TARA. And here would be more external resources about security standards. I mentioned, for instance, the CERT rules for robust coding. I mentioned also the results of or the usage of these external vulnerability databases. And so that would be also available to you afterwards. So make sure that you train. That's my last takeaway, which I want to pass on. Train your people. Because security is really about thinking about the negative, and that applies to the whole community. Often managers would ask us, so who do I have to train? Security manager, maybe some IT security expert. And I was tell them, no, you have to train really the whole amount of people, because the first and most dangerous vulnerability is social engineering. Social engineering means that we are, let's say, asked for some support and inadvertently just give away more and more information. And it happens everywhere. And that means we have to be prepared for social engineering. That can be spam, that can be phishing, that can be all sort of nice gifts, or people would just approach you on a technical conference. So be prepared for the worst in order to protect your own environment. Now, another way to learn more, we have our annual Vector Forum next year, 29 June, where we bring a lot of topics into what we call converging systems, the convergence of IT, enterprise IT, and product IT. And that would be also a lot of learnings from key players in the market. Just join if you're interested. That brings me to the end of this presentation, and I'm sure you might still have some questions, which we have a few minutes to address.
Question we did have, and I might say this incorrectly, I apologize. Do you leverage something like is it Mitra, MITRE, Mitra's attack inventory of attack tactics, techniques, and procedures to do your Tara. Does that make sense?
Yeah, that short answer would be that's one of these, let's say, techniques which I mentioned when we look into what are known vulnerabilities. Known means to specific groups which really are experts, and we utilize whatever is available because that's exactly the benefit which we bring. But I mean, the logic is very simple. Each hacker would use it because it's somehow public domain, so we will also use it.
Christof, thank you so much for your time and for presenting with us.
Thanks, Susan. Thanks, everybody, for staying, and wish you good success with your security and your systems.